This video is about geometric interpretation of definite integrals. We'll focus on the area interpretation, and we'll talk about properties of definite integrals. And then we'll use the area interpretation to evaluate definite integrals. As you can imagine, this definite integral, which is represented by the limit of a Riemann sum, is closely related to area. If your function is continuous on the interval from a to b, and it's non-negative, so that means the function is just greater than or equal to 0 on the interval from a to b, then this area, the area between the function y equals f of x and the x-axis, between x equals a and x equals b, is given by the value of that definite integral. So that area pictured over there is the integral from a to b of f of x with respect to x. Now, x is just a dummy variable. Really, we could say that this y is a function of t instead. Now I just have f of t dt. It's just a placeholder, but we're basically taking that function and we're multiplying it by a tiny width, and then we're adding all of those together, and we've got infinitely many rectangles, or alternatively, all the rectangles are going to 0, or all the widths of those rectangles are going to 0, and that's giving us area. Now, if the function is sometimes negative, we can't interpret it as area, but we can interpret this as net area. A definite integral always represents a number. That number could be positive, negative, or 0. If that function is greater than or equal to 0, like this, and it's continuous, then that number is area, and area is, of course, positive. But let's say that f is continuous and f is sometimes negative. Then the integral from a to b of f of x with respect to x is going to be the area above the x-axis. That's the area bounded by the function f of x and the x-axis that lies above the x-axis, minus the area below the x-axis. If you're saying to yourself, there's a lot of area below the x-axis, you're absolutely right. Let me be more specific. I'll draw you a picture. So let's say your function looks like this. And at x equals a, we're over here. And at x equals b, we're over here. So our function is sometimes positive and sometimes negative on the interval from a to b. There's some area between the function and the x-axis that lies above the x-axis. That's this area. I'm going to label that with a sub 1. If I draw all of those little rectangles and I multiply by those widths, delta x sub I, that we see in our Riemann sum, and I add them together, well, that's going to give me a positive number. It's going to give me the area of those, the areas of the rectangles approximating this area, the area under the curve. Now over here, we're going to do the same thing, but the function values that we're multiplying by are negative. So it's going to be an area, but times a negative 1. So this area that's below the x-axis gets subtracted from that area above the x-axis. And if they happen to be the same, your integral could equal 0. So if this area is larger than this area, your definite integral might be a negative number. If this area is larger than this one, then the definite integral will be positive. If they happen to be the same, then you could get 0. So this is sort of a net area interpretation. Area is always positive. Definite integrals can be positive, negative, or zero. But if we're interpreting it as area, we want to think of it as a net area. It's the area bounded by the function and the x-axis. It's the area above the x-axis minus the area below. And if there was some parts, if it was above the x-axis, then below, and then above, and then below, and we could just keep doing that. We add all those areas that lie above the x-axis, and we subtract all those areas below, and that will give us the value of the definite integral. Okay, so now let's look at some other properties. Now we know how to interpret a definite integral as area. I think this one makes a lot of intuitive sense. If your function is well defined at x equals a, here's y equals f of x, and there's x equals a. Like, what's the area under the curve from x equals a to x equals a? Well, I don't think there's any area there, because you kind of start and stop in the same place. There's no x, there's no dimension over here. So this is 0. It's always going to be 0, provided that that function value is defined there. Now, if the integral from a to b is well defined, then you can flip these. So instead of having the integral from a to b, you can write the integral from b to a, and that will work as long as you add this negative sign there. Then we say, if a function is integrable on the integral from a to b, and a to c, and b to c, or c to b, it's integrable on all the intervals that are implied by these limits for x values, then this is equal to this. Now let me draw a picture for you. Let's say that x equals a is here, x equals b, or x equals b is over here, and c is a number in between. This is y equals f of x. What we're saying here is that the integral from a to b, which represents this area, is equal to the integral from a to c. So that's this area, whoops, plus the integral from c to b. And the integral from c to b is that value over there. Doesn't it make sense that the area under the curve from a to b would be the same as the area from a to c plus the area from c to b? I think it does make sense. Notice the way that these are arranged though. I've got a as my lower limit here, and my b is my upper limit over there. So we go from a to c, that's the middle one, and then from c to b. Now this property actually holds if the numbers aren't necessarily in this order, because this number at the top does not necessarily have to be larger than the number at the bottom. Usually it is. Usually we integrate from a to b, and that's a smaller number and that's the larger number, but we could flip it and then just multiply by -1. This holds all the time, but this is sort of the way I think through why it holds. It turns out that using this property, we can show that this continues to hold even if A, B, and C aren't listed in this order that I have over here on the right. Okay, so this is the integral from A to C. That's in blue. The yellow one is the one from C to B. And then the original one, that's the whole thing. Okay. Now these are just extensions of those properties that we had for summations. Remember whenever we said before, if you've got a constant times the sum as I goes from 1 to n of a sub I, you could factor out that constant. That still holds over here, but remember these definite integrals are defined as limits of sums that look like that. So we could pull the constants out from those limits as well. So if you have a constant times f of x in your integral here, that's called the integrand. The function inside is called the integrand. If you've got a k inside your integrand, you can take that out, and you'll just have k times that integral from a to b of f of x dx. Now, if I'm adding two functions here, because of the properties of our summations, I have a sub I plus b sub I here. Well, I can write that as the sum of the a sub i's plus the sum of the b sub i's. That's legal. Well, remember, these are defined as limits of sums that look like this. So if it's legal for the sums, it's also legal for the definite integrals. The integral from a to b of f plus g is the integral from a to b of f plus the integral from a to b of g. And you could subtract those as well. And then we've got a couple more properties, and then we'll be done with the properties. Now, if our function is integrable, and our function is greater than or equal to 0 on the interval from a to b, so maybe it looks like this. And that's a, and that's b. Well, in that case, we're guaranteed that the integral from a to b is going to be positive. If the function happens to be 0 the whole time, we get 0. Yeah, so if f is a non-negative function, the integral from a to b of f of x dx is also non-negative. Now this one makes intuitive sense as well. If f is less than g for each x between a and b, so say I've got y equals g of x up here and y equals f of x down here, and you're on the interval from a to b, so x starts at a over here and x ends at b over here. We've got that and that. Well, this says that the area under the curve for the function f of x, so that's the integral from a to b of f of x dx, that's this area. Well, if that function is less than this function, well then of course the area under this curve, the area under g of x, that area, that includes all of this, that area is greater than that yellow area. I think we can all see that. Okay, so those are our properties. Now, we want to remember that this definite integral represents area, and so we want to look at some pictures sometimes and write a definite integral that represents the area. Okay, so let's look at this first one. It says write a definite integral that represents this area. Well, I noticed that x is starting at 0 and ending at square root of 5 for this picture, for that area. So I've got the integral from 0 to square root of 5, and then I'll have a function multiplied by dx. Well, the function there, the function that's bounding that area, is y equals 5 minus x squared. So that's what we've got there. Now this one is a little trickier because we aren't necessarily going to write an integral with respect to x for this one. We're going to write an integral with respect to y, and you might be saying to yourself, why would I do that? It's because that area that is shown here, it's against the y-axis rather than the x-axis. Over here, one way that I can think about this is I can think about drawing these little rectangles like this. I'm taking that y value and I'm multiplying by a tiny dx, tiny delta x there. So that's my f of x sub I. So it's my f evaluated at a particular x value times delta x, and then we take the limit as the norm of the partition approaches 0, and that gives us this. Since it's continuous, it's the same as taking the limit as the number of rectangles goes to infinity, and this represents the area. We want to do the same thing here, but you're just, instead of drawing your rectangles vertically like that, you want to draw your rectangles horizontally. Now the width of that rectangle isn't delta x, that's a tiny distance in the x direction. The width is a tiny distance in the y direction. So we can do this, it's totally legal, except instead of a dx over here, I'm going to have a dy. This is a little tricky. Now y starts at 0 and goes to 2, so those are my limits of integration. Now typically you want to write the function here, but be careful, it's not y equals square root of x. It's this x value. It's that x value, but it's written in terms of y. So we need to take this equation that has y as a function of x and solve it for y, or solve it for x as a function of y. So we square both sides, and we get x equals y squared. So that's our height. When x is 0, y is 0. When x is 1, we get, or when y is 1, we get x equals 1 squared. When y is 1/2, we get x equals 1/2 squared, or 1/4, and so on. When y equals 2, x will be 4. So that rectangle would have a height of 4 at that point. It's like I'm doing a Riemann sum, but I'm turning those rectangles on their side. So we take x as a function of y right here. This was y as a function of x. Instead, we're doing x as a function of y. That one's a little tricky. I'm more concerned that you can evaluate, or you can turn this into an integral. Okay, now over here, we've got something similar. We've got an absolute value function, and we're asked to write this as a definite integral. Well, the absolute, we want the area under the curve, the area between that function y equals the absolute value of x minus 1 and the x-axis between x equals 0 and x equals 3. So I'd write the integral from 0 to 3 as I start there and I end there of the function times dx. And that's it. Okay. Now, sometimes you're asked to evaluate integrals, and we don't want to have to use the limit definition every time. We're going to have a shortcut for that in the next section. But in this section, we can use area formulas. This one says, use geometric formulas to evaluate the integral. Well, in order to do that, I need to visualize this first. So I would draw the curve given by y equals 8 minus 2x. We're going to sketch the region. And then once we look at that region, we'll see what formulas are appropriate to find its area. Now this is not to scale probably, but I want to sketch y equals 8 minus 2x. Well, I know right away that's a line. When x is 0, y is 8. When y is 0, we get 8 minus 2x is 0. So 2x has to be 8, so x must be 4. We get a line that looks like this. And we're asked to find the value of this integral. Well, that represents the area under this curve, given by y equals 8 minus 2x, between x equals 0 and x equals 3. So at x equals 3, we're right here. And I want this area. Well, there are a couple of ways you can find that area. We could find that area by subdividing this. I could say, well, and of course this is not to scale, let's find the area of that little rectangle and then take the area of this triangle up here and then add them together, and that will give me the value of the definite integral. Or you could find the area of the larger triangle and subtract the area of the smaller one. Either one should work. So let's figure out what our function value is when x equals 3. When x is 3, x equals 3, y is equal to 8 minus 2 times 3, so y is equal to 2. Okay, so if I am finding the area of that triangle at the top, that's 1/2 base times height. And this rectangle in the bottom is just going to be length times width. Now the base is 3, because we're going from 0 to 3. And the height is, well, that's 8 minus 2, so that's 6. And then over here for that little rectangle, we get 3 times 2. And then you just add. 2 goes into 6 3 times, so we've got 9 plus 6, which is 15. That's the area. Now you could have also found the area of the larger triangles and subtracted the area of the smaller triangle. Let's just do that to confirm that we get the same answer. So the area of the larger triangle is 1/2 base times height. Base is 4, that height is 8. And then we'll subtract 1/2 base times height for that smaller triangle. The base is 1, the height is 2. So we get 1/2 of 8 is 4, so we get 16 minus 1, so we get 15. Do we get 15 either way? We sure do. So that area, that blue area right there, that's 15 square units. And if I want area for this guy, these guys are harder because they're curved. Then I'd have to use the limit of a Riemann sum or an upper sum or lower sum, like we talked about in previous sections to evaluate those. So we're going to wait for the shortcut in the next section to evaluate those integrals. But for this one, I can use area formulas as well. It's just the area of that triangle plus the area of that triangle. So I have 1/2 base times height. That's base is 1, the height is 1, plus 1/2 base, which is 2, times height, which is also 2 over there. 2's reduced. So we get 1/2 plus 2, 2.5 is our area there. Oops. So it's not too bad if it's a geometric shape that you're familiar with, like a rectangle or a triangle or a semicircle or a circle. You can find the area using those formulas that you're familiar with, length times height, pi r squared, 1/2 base times height, and so on. Okay, so let's do one more example where we use that idea. I like this example because it also includes area below the x-axis. So let's do everything. Let's do these here with a couple of assumptions. We'll assume that that's a line, that's a line, that's a line, and assume that this is a semicircle of radius 2 centered at the origin. Okay, so I've got the integral from 0 to 2 of f of x dx, and this is the curve f of x. So I want that area, but since it's below the x-axis, it has to be counted as negative. So we'll have a negative value, and it's 1/4 of a circle. So I need the area of 1/4 of a circle, and so that's going to be 1/4 of pi r squared, where the radius of the circle is 2. So we have negative 1/4 of pi times 2 squared. The 4's reduced, and you get negative pi. That's that value. Okay. Then we're asked for the integral from 2 to 6 for this function. Well, that's just a triangle, so we can use 1/2 base times height. The base, that's the distance from 2 to 6, that's 4 units. That height is 2 units, so it's 1/2 of 4 times 2, so that's 4, okay? Then I've got the integral from -4 to 2 of this function. This is going to be negative because it's going to be this area and this area and that area, just going from -4 and ending at 2, but notice that it's all below the x-axis, so we have to count it as negative. So we find the areas and then we multiply by -1. Well, I've got the area over here. It's going to be -1 times 1/2 base times height. The base has a length of 2, the height is 1. And then I've got a semicircle from -2 to 2, and that circle has a radius of 2. So the area is 1/2 pi r squared, but we're counting it as negative because it's below the x-axis. So I've got, so that's all correct, but r is 2, so we've got these reduced, so we get -1, and we have -1/2 of pi times 2 squared. So one of those 2's will reduce, and we get -1 minus 2 pi. So that's that right there. Okay, now this one's kind of fun. I really like this one. It says, find the integral from -4 to 6 of the absolute value of f of x. Ooh, absolute value of f of x. Well, absolute value of f of x looks exactly like f of x when f is positive, so it's going to be exactly the same as this over here. And earlier we calculated this area, and we said that that area was 4. And we calculated this area, that was the area of a semicircle. It turned out to be 2 pi. That's this part and that part together. And we found this area over here, and it happened to be 1. Okay. Now when I'm finding the area under the curve for the absolute value of f of x, everywhere that this function is negative, I have to multiply it by -1. It just flips the whole thing up. So we want this area plus this area plus that area. And we know that this area is 1 because that area is 1. And we know that this area is 2 pi because that area is 2 pi. So the answer for part D is just 1 plus 2 pi plus 4. So it's going to be 5 plus 2 pi. Now this last one is the integral from -4 to 6. So that's the whole thing. And then we're taking 3 times our function and subtracting 2. Ooh, this is a little bit harder. So I want to take this function right here, and I want to stretch it by a factor of 3. So it's going to be 3 times taller. And then I want to subtract 2 from that and integrate from -4 to 6. Now this might be easier if I think of it as, or if I use my properties to evaluate this. So first I notice that I've got two terms, so I can split this in this way. This is the integral from -4 to 6 of 3 times f of x minus the integral from -4 to 6 of 2. That is something I can find because I can draw that. And this I can find by factoring out that 3 and then looking at the area under the curve, or the area between the function and the x-axis between -4 and 6. So let's do that piece. I like this problem. So we'll factor out the 3. And you've got the integral from -4 to 6 of f of x now. And this integral from -4 to 6 of 2, we're going to evaluate that in just a minute. So I've got 3 times this value, and this can be found by looking at that net area. It's area above the x-axis on the interval from -4 to 6 minus the area below. So we've got 4 minus 1 minus 2 pi. So that is the integral of f of x on the interval from -4 to 6. It's 3 minus 2 pi. And if this function is stretched by a factor of 3, it's 3 times as tall. It turns out the area, or that net area, is exactly the same as it was before, but times 3. So we've got 3 times 3 minus 2 pi over here. Now this one isn't pictured there, but we could draw it. So I'm going from -4 to x equals 6, and I want y to equal 2 the whole time. So there's my function, y equals 2, and I want that area. Well, that's just a rectangle. The length is 10. 6 minus -4 is 10. And then I'm multiplying it by that height of 2. So we're subtracting 20 from this. So we have 9 minus 6 pi minus 20, and that ends up being -6 pi minus 11. And that's the value of this integral over here. So we had to use our geometric formulas for area. We had to use that property that we can factor out the 3. We had to remember how to get this. Since it's just a horizontal line, we could draw the picture and find the area that way. Now we'll also have shortcuts that involve antiderivatives for evaluating this and this. But in the cases where the area is a triangle or part of a triangle, or a rectangle in a triangle, or triangles and semicircles or rectangles, all of those integrals, all of those definite integrals can be found using the formulas that you've previously studied. So make sure you understand definite integrals represent area under the curve. If that function is positive all the time, that's the area between the function and the x-axis between x equals a and x equals b. Now, if the function's sometimes positive and sometimes negative, you take the area above the x-axis and you subtract the area below. So this definite integral could be a positive number, a negative number, it could be 0. But we're interpreting it geometrically as this net area. It's the area between the function and the x-axis, and it's the area above the x-axis minus that area below. So keep that in mind. In the next video, we will talk about how to evaluate this when that is a curve and our geometric formulas don't apply. It turns out that it's related to antiderivatives, which seems just amazing. I love the fundamental theorem of calculus. But we'll talk about how area is related to antiderivatives in the next video.